and the solar geophysics, satellite navigation systems, remote sensing applications, human spaceflight, the Indian context. We are proud to host the participants from multiple countries representing diverse academic, research, and industrial backgrounds, all united by a shared commitment to advancement, knowledge exchange, and global cooperation. Over the course of this conference, we will engage in the thought-provoking sessions, keynote addresses, and panel discussions led by the foremost leaders in their respective fields. We encourage you all to actively participate, to engage, question, share, and network, for it is in these interactions that we find inspiration and form lasting collaborations. I would also like to take this opportunity to thank our sponsors, the organizing committee, and the dedicated volunteers whose tireless efforts have made this event possible. Your contribution is deeply appreciated. Once again, I extend a warm welcome to you all. May this conference be a fruitful and insightful experience to everyone. Thank you.
Thank you so much, ma'am. Research and development lay the foundation for innovation and progress. To provide insights into the theme of our conference and the proceedings that lie ahead, I now welcome Dr. M. Kannan, our respected Dean of R&D, to release these proceedings.
So good morning to one and all present here, and also welcome the dignitaries honored of the dais. So I take privilege in addressing about the United International Conference on Technologies for Research, Product Developments, and Space Science. And the name we have coined as UICon, so that will be a stable coin in which, based on the theme of the conferences, the further terms will be added. So now the theme here is on technologies related to the research, product developments, technologies, and space science. Okay. So this is how we have termed, and we hope that every year, so we plan and execute this conference with the different editions. And here, this conference is a joint venture. So two collaborators are there. Say one is Sigi University. It is from Kuala Lumpur, Malaysia. So we signed MOU with them a couple of years before, and we are performing various activities under this collaboration. And that university greatly supported us and act as a collaborator for this conference. And this is a very old university. It is started during the academic year 77. And almost more than 16,000 students are studying, and in Malaysia they have almost 5 branches are there, and they are concentrating on the engineering discipline, technological discipline, and built environment. Okay, so this is one collaborator we are proud to tell, and the another collaborator here is the ISRO Space Center, ISRO Space Tutor Center. So I think we have launched this ISRO Space Tutor Center some 6 months before, and ISRO is promoting space education, technology, research through this center. So almost in India, 181 centers are there. ISRO Space Tutor Center, that is a registered center, and only few institutions got that registration. So if you take in Tamil Nadu, almost 17 ISRO Space Tutor Centers are there, and only few academic institutions are part of it, and we are proud to tell that they are also one of the collaborators for this international conferences. So these two collaborators greatly supported us in various means to successfully launch and to conduct this international conferences. And theme of the the various topics covered by the conferences is already disclosed in the welcome address, and mainly 3 areas we are concentrating. One is engineering, technology, and very importantly here is the space sciences. So equally we received papers from all these 3 disciplines appreciably. And here, So most of the promotions we have done through the digital partners. One is Technical Symposium, then Nova Fest, and the conference hall. So these are the three few of the promoters in which our conferences, brochures, and other information reaches in and around India. And with this support, so we got appreciable number of papers, articles, and participants through this event. And the organizing committee is constituted by all the heads of the department and the vice principal. So they have contributed a lot to launch these international conferences in a successful manner. And the advisory committees, so we have advisory committees. The advisory committees are Dr. Kaujan, Secretary General of UNICEF Global. Then another one is Shuk Hon. He is from Japan Aerospace Exploring Agency. Then Dr. M.V. Ramana, Head MPS MRID Spacecraft Mechanism Group. Then we have other 4 contributors also there. So they have actively participated to evaluate our papers. So they greatly supported us. And 2 keynote addresses are there. So one is by the chief guest, Dr. Chandrasekharan sir, and another chief guest is from Dr. Chan Myoki. He is a deputy dean of R&D from Segi University. Okay, and there are almost 120 plus papers we have received from India and also from abroad, and almost 116 papers are from India, and so 5 to 6 papers we have received. The research papers we received from Malaysia, and actually the 63% of the papers we have accepted to be published in our international conference proceedings with the ISBN number. And also we are proud to tell that a lot of reputed institutions who have actively participated and promoted their students and faculty members for these international conferences. To name a few, one is Annamalai University, Government College of Technology Coimbatore, PSNA College of Engineering, Ramco Institute of Technologies, Kumaraswamy College of Engineering, JPR Engineering College, DMI College of Engineering, Avinashilingam University, Puducherry Technological University, Sri Ishwar Colleges, to name a few. These are all some of the institutions they greatly participated. I hope that almost 40 to 45 institutions they have promoted their students and faculty members to join this conferences. And the jury committee, actually we are having 4 sessions. One is 3 sessions. One is through online. Almost some 18 papers we have received to present through the offline, and through the online we have 2 jury peoples are there. One is Dr. Rajeshwari. He is a professor from AIDS department from NGP College of Engineering, and another one is from Dr. Arun Kumar. He is an associate professor from the department of AIDS from Ishwar College of Engineering. So they will serve us to act as a jury to evaluate, assess the papers submitted through the online and offline. Okay, and also we are providing the conference certificates, online and offline conference certificates, duly signed by the international person as well as from our institution also. And also we hope that for the past 3 months we are working to attract more participants, and appreciably we received 120 papers. It's very happy, and also the acceptance ratio is 63% after the advisory committee comments. And we hope that the subsequent conferences we will successfully will plan and execute in association with IEEE and other partners, because partners are very important in order to pull papers from internationally. So during the subsequent we will do all those things and we can make it more success. And I thank all the participants for coming over here as well as joining the conferences through the online. And I tell best wishes and all the best for your successful presentation. Thank you so much for the opportunity given by the organizing committee. Thank you so much.
Thank you, sir. An event of such grandeur deserves to be highlighted. To shed light on the key aspects of this conference, I invite Dr. P.C. Induja, HOD of CSE, to explicate the highlights.
Good morning to one and all present here. A hearty welcome to all the participants online and offline for this UICon TRPDS 25. So today marks a proud and pivotal moment in the journey of UICon TRPDS 25. What we are about to unveil is more than a publication, a testament to innovation and collective intellect. This conference proceedings that we release today are the crystallized outcome of days. Each page represents a spark of curiosity. Ladies and gentlemen, it is with great pride we officially release the UICon TRPDS 25 conference proceedings. I request the Chief Guest, Dr. Chandrasekhar, to release the proceedings, and this will be received by our beloved Principal, sir. Please give a great round of applause. Thank you, sir. And another feather on the hat for UIT. UIT is certified and acknowledged as the life member of the Society of Indian National Society for Aerospace and Related Mechanisms. So we are really happy to receive that certificate, requesting the Chief Guest to again give away this certificate to our beloved Principal, sir, our Academic Director, ma'am, and Dr. Ashok Gopalakrishnan will receive the same. Thank you, sir. Thank you all.
Thank you, ma'am. A great day begins with the great thoughts. To begin this great day to be greatest, I take immense pleasure and privilege to honor or introduce our chief guest, Professor A. Chandrasekhar, an esteemed expert from the Department of Earth and Science at IIST. His insights on motivation are sure to inspire us all. Welcome, sir. The stage is yours.
Okay, let me at the outset, good morning to all. Let me at the outset thank the organizers for providing me this opportunity to share some of my thoughts as part of the presentation to all of you. And for these dignitaries on the dais and off the dais, I'm extremely humbled by this invitation. I'm really happy to see a large number of girl students here. I was told that we have 600 girls and 250 boys, but it looks like 90% of them are girls only. So it's a very good thing. And so what I will be talking about is, I think we have already lost some 20 minutes, so we are behind the schedule. I have been part of this Indian Institute of Space Science and Technology for the last 16 years. and prior to that I was at IIT Kharagpur. So my journey in academics is about 37 years now. And so without much ado, let me start the presentation. Not this is biodata. PPT. So when I was invited to this conference and I was contacted, I was told that I need to speak something on computers and space technology. Now, as part of as part of the academic faculty of the Indian Institute of Space Science and Technology, we are part of the space science community, and I'm happy to note that space science is also an important component of this conference. And being an atmospheric scientist, I thought it would be the best to actually connect atmospheric science with space sciences and the sort of importance space science, the applications that it has provided for the development of the atmospheric sciences subject. And towards the end, I will also touch upon the role played by computers in the development of atmospheric science. So as the title goes, I'm going to talk about satellite applications, satellites which are essentially the payloads that are launched by the launch vehicles as part of the space technology programs. So atmosphere and oceans are both fluids. Okay, the oceans are liquids, our atmosphere are gases, but then both of them have this common property of fluids. So because of that, the space science finds applications in both atmospheric sciences and ocean science. Next one. So the contents are, I'll just touch upon small aspects of meteorology satellites, and essentially I would want to focus on two things. One is how satellites and space technology is helping us determine the sea surface temperature. As we all know, the surface area of the Earth is covered by almost 3/4, like about 70-75% of the surface area is covered by oceans. And oceans, we don't have any conventional observations. And hence, it's all the more important to obtain information of the ocean, the state of the ocean, and its various features and characteristics from satellites. So the most important property of the ocean is the sea surface temperature. And I will just touch upon how the satellites are helping us find this very important property of the ocean. Next, I will dwell on the vertical temperature profile of the atmosphere, how the satellites are essentially helping us find this. I'll just touch upon very briefly on the physics principles, and without much mathematical rigor, I will just touch upon the essential facets of this association. Then towards the end, I will talk about the role played by computers in weather prediction. Next one. So we all know satellites are meteorological satellites. Essentially, the first meteorological satellite was launched on 1st April 1960. In the last 65 years, there has been tremendous advancements in various payloads that measure the various facets of the atmosphere in the oceans. And these have made a profound impact on our capability of weather prediction today, both in terms of the atmosphere as well as the ocean state forecast system. So satellites have played a very pivotal role in the development of this science. So we all know that essentially we can broadly divide the orbits that encompass the meteorological satellites into two. One is the polar orbiting, which is a near north-south orbit, which is passing through the pole, North Pole and the South Pole. And typically these are low Earth orbits. So typically they can be around 800 kilometers above the surface of the Earth. And typically the period, orbital period would be something like about 90 minutes. And these provide global coverage because the satellite will be going along in the vertical plane, south to north, and then ascending in the descending phases of its path. And then underlying Earth is going to rotate. We all know the Earth rotates at the rate of like one rotation in one day. So in about an hour, the Earth rotates 15 degrees to the east. So the rotation is always from west to the east. And the satellite, as it goes through, the Earth is rotating underlying the satellite. And so it's able to provide the global coverage. This is a very important polar orbiting satellite. And out of this polar orbiting satellites, orbits, most of the meteorological satellites use what is called sun-synchronous orbit. Now it is very important that when a satellite passes a particular place on the Earth, the illumination of the sun on that place should have the same angle. So the illumination should not change. Like today I have one particular illumination angle. Tomorrow when the satellite passes, the sun's illumination angle is different. So the sun illumination angle changing day by day and with every pass is going to introduce its own uncertainty into my meteorological data, and so I don't want that. So I want to keep the effect of the sun constant. So it should not impact my meteorological data. Essentially what the sun synchronous orbit allows us to do is, when the satellite passes a particular place on Earth, let's say, suppose it crosses equator and we are in a location at equator. So what happens, it crosses at the same local mean time. That essentially means that the location of the sun in the sky is going to be the same as the satellite passes every day. So every time the satellite passes that particular station, the location of the sun is going to be the same. That is ensured by the sun synchronous orbit, which ensures that the variability introduced by the location and the illumination of the sun is taken away from your data. So the next important orbit is the geostationary satellite. Now we all know that the polar orbiting satellites traverses in a north-south orbit and can provide global coverage, but then it cannot provide you useful, more temporal resolution data over most of the regions. And that's provided by the geostationary satellite, which are put in an orbit around over the equator at a height of close to 36,000 kilometers. All of you know this. So it can provide you information of the atmosphere and the underlying ocean. Roughly every 20 minutes you can get an image. And because of this, we will have frequent information of the atmospheric as well as the oceanic system from geostationary satellite. And these are the two. So one is giving you more temporal resolution because it's height of 36,000 kilometers. So it has the same orbital period as that of the Earth. And so essentially the satellite appears to be at a particular fixed longitude over equator with respect to all the positions in the Earth. So typically it has been estimated that if you launch 5 geostationary satellites at different longitudes over equator, this can provide you almost global coverage, something like 50 degrees south to 50 degrees north. And this is a very important contribution to our knowledge of atmosphere and ocean. So the next one is, you can go to the next. I've already touched upon the geostationary orbit. You can go to the next one. So the underlying physics is basically the black body radiation of Planck's. So Planck gave the very famous black body radiation formula that is given at the top. B lambda, that's called the Planck radiance. Lambda is the wavelength, capital T is the temperature, so it's a function of both wavelength and temperature. And C1b, C2 are constants that involve the Planck constant, that involve the velocity of light, that involves Boltzmann constant. And so this is this very interesting story behind this. So before Planck actually gave this formula in 1900, and he was possibly one of the first physicists to get the Nobel Prize. He was a professor in Germany. So before him, there was a formula for the radiance in the long wave portion of the electromagnetic spectrum, and another formula in the relatively short wavelength part of the electromagnetic spectrum. What essentially Planck did was he found a formula that fitted both these limiting cases, both the short wavelength as well as the long wavelength. But then that's not research. And he actually performed very careful experiments over the entire spectrum of the electromagnetic spectrum. And he could find that the formula that he had actually proposed was sufficiently accurate to explain the entire wavelength of the electromagnetic spectrum. However, that's not research, I was telling you. You just find a formula and then that doesn't enhance our knowledge. So he has to give a physical reasoning why this formula is correct. And then this concept of quantum physics came. So that's a very, very important development in modern physics. So almost all, so when we usually will deal in satellites treating atmosphere, ocean, we'll be mostly dealing with the thermal infrared part of the electromagnetic spectrum. Infrared, as you all know, is visible is from 0.4 micrometer to 0.7 micrometer. Any wavelength greater than the visible is called infrared, until something of the order of 1 meter. I mean, there are a lot of ECE students here, so I should presume that they know what I'm talking about. And wavelengths less than 0.4 micrometer would be called the ultraviolet. So we'll be talking mostly discussing the thermal infrared portion, because typically the average surface temperature of the planet Earth is around 15 degrees centigrade, which works out to 288 Kelvin. Now there's one of the important formulas in quantum modern physics is Wien's displacement law, that tells us if you know what is the average black body temperature of a radiating body, you can find out what is the wavelength at which you have maximum energy. So that turns out to be 10 micrometer, which lies in the thermal infrared portion. So that's why we are going to concentrate on the thermal infrared portion. And in this thermal infrared portion, it's very convenient for us to ignore scattering of light, which introduces a major, I wouldn't say complication, it introduces many major effects into our derivation. So, can you go back to the next one? Yeah. So you can go back to the next few slides and I'll be coming back to this. Okay, so in essentially the last, so what we have done is, we have a radiometer in the satellite, okay, which measures radiant energy coming out of a particular wavelength. Okay, now I can invert the Planck radiance formula which we saw in the previous slide and obtain, if I know what is the measured radiance, and if I assume that the measured radiance is the same as the Planck radiance emitted by a black body, which is perfectly acceptable in the thermal infrared portion of the electromagnetic spectrum, I can just reverse that same expression and find out T. For a given particular wavelength, my radiometer is going to measure the radiant energy in different wavelengths. So for a particular wavelength, I measure what is the radiance. The only unknown is the temperature. So I can find out what is the temperature. So this is, in essence, this temperature is what's called the brightness temperature. So when I say we want to find out the sea surface temperature of the global ocean, this is what we should use. But then there is a small issue. Now, how do you know? Now we have the planet Earth. 70% is covered by the surface area of the ocean. The remaining 30% is covered by land. Now the radiometer in this satellite cannot distinguish whether the radiation is coming from the ocean or it's coming from the land, right? It cannot distinguish because typically the temperatures will be similar. So how do we distinguish and say this data corresponds to ocean? This doesn't. The only way it can be done is because oceans are huge thermal reservoirs. You can keep putting more and more energy and they're going to keep storing this energy because they are huge thermal reservoirs. And they're not going to show much difference in temperatures in space as well as in the temporal scale. So if you look at data over, let's say, several hundreds of kilometers, and then the temperature, the brightness temperature doesn't change markedly, then obviously we can infer that it's going to correspond to ocean. Whereas over land, because you have undulations, you have orography, you have many other things coming into play, you have rivers, so the temperatures are going to be not so homogeneous when it comes to the horizontal space. Okay, so this way you can distinguish between ocean and land temperature. Now I can have ocean, I can have a cloud over the ocean, the cloud top can radiate. So the radiometer in the satellite can detect this radiation, and how does it know whether it's coming from the ground or coming from the ocean's surface or whether it's coming from the cloud top? Now the question is, the cloud is at a height, depending on whether it's a low cloud, medium cloud or high cloud. So its temperature is going to be markedly different compared with the ocean sea surface temperature. So from the actual magnitude of the brightness temperatures that we derive, we can estimate whether it is actually the brightness temperature corresponding to the ocean or the brightness temperature corresponding to a cloud top. Okay. So in addition to that, we also have some other difficulties. Essentially, in the thermal infrared portion of the atmosphere also absorbs whatever is radiated by the Earth's surface, including the oceans, is absorbed by the atmosphere. Atmosphere has constituents like CO2, like O2, like H2O. All these things have very strong absorption bands in various thermal infrared portion of the electromagnetic spectrum. And we all know from Kirchhoff's law, which states in physics, every good absorber is a good emitter. So if you have a constituent which has a strong absorption in one particular wavelength, it is also going to strongly emit in that same wavelength. Now, if I have an overlying atmosphere which absorbs the radiation coming from the ocean and in turn re-emits, it's going to re-emit at its own temperature, which is going to be lower than the sea surface temperature. So if my objective is to determine the sea surface temperature from the satellites, I need to use that wavelength in which the atmosphere is completely transparent. Essentially, the atmosphere is not going to absorb any of the radiation coming out in that particular wavelength. Such a wavelength band is what's called an atmospheric window. It extends from 8 micrometer to 12 micrometer. Typically, there is very few absorption in the atmosphere happening over that, and that's why it's called a window. So essentially, if I use a radiometer in the satellite and I measure the radiant energy coming out in the atmospheric window region, then I can be sure that this is not contributed by the atmosphere. It is coming from the Earth's surface or from the cloud drop. To distinguish between ocean and ground, land, I said how we can distinguish. To distinguish between ocean sea surface temperature and the cloud top temperature also, depending on the actual magnitude difference, we can again find out which is the ocean related. So, to find out the ocean sea surface temperature, we need to use radiation. We need to measure them in the radiometer in the satellite over a wavelength band where the atmosphere is completely transparent. It is not going to absorb any wavelength. On the other hand, can you go back? Go to the next slide. So these are all what I said. Next one. Okay, so the bottom panel is basically, you have written 5790. That's the Planck radiation formula for a black body temperature having a temperature of 5790, which corresponds to the temperature of the sun. And 289 Kelvin is 289 Kelvin is the one corresponding to the average temperature of the planet Earth. So you can see x-axis is the wavelength in micrometer. So the Planck black body radiance from sun and the Planck black body radiance from the Earth have no overlap virtually. So you have radiant energy from the sun coming only up to 4 micrometer. The energy from the Earth starts from 4 micrometer and goes to about 100 micrometer. So there's no overlap between the Planck black body radiance from the sun and the Earth. The second important thing is, once I change the temperature, then the Planck body radiance will change. That we have seen from the expression. For a fixed wavelength, if I increase the temperature, the radiance would increase. So that is given by the right panel figure, which shows what is the black body Planck radiance for different temperatures. You can see 7000 Kelvin, 6000 Kelvin, and 5000 Kelvin. And the left panel tells you, suppose I have a layer of atmosphere. I have a certain amount of incident radiant energy, R lambda, that corresponds to a particular wavelength. If part of that is reflected, that part of the radiation is called RD. Small r is the reflectivity or the reflectance. How much of the incident radiation is reflected. The remaining part gets into that layer. Part of that radiation gets absorbed and the remaining gets transmitted. So the one that is transmitted is tau lambda, capital R lambda. That's the amount of radiation that gets transmitted through the layer. And the remaining part is the amount of radiation that is absorbed. A lambda, R lambda is equal to the total incident radiation minus the radiation reflected minus the radiation transmitted. That is exactly what is the amount absorbed. And for a black body, the amount of radiation that is absorbed is going to be exactly equal to the amount of radiation it is emitting. So there the absorptivity is going to be radiative introduction. Next slide, please. Okay, so this is what's called the radiative transfer equation. So L lambda is the radiance, it's the radiant energy received by the satellite, the radiometer in the satellite. And I have the first term, that is the surface contribution. And the second term is the atmospheric contribution. So when I want to determine the sea surface temperature of the ocean, the contribution is going to come only from the first term. So I'm going to choose wavelengths, that is the wavelengths within the atmospheric window, that are going to make the second term 0. Because the second term involves, inside the sigma summation, you see emissivity. Emissivity is equal to absorptivity. So in the atmospheric window, no atmosphere is going to absorb anything. It's going to be completely transparent. So that means absorptivity is going to be 0. So emissivity is going to be 0. So the second sigma term is going to be 0 if I want to determine sea surface temperature. So I can use the radiative transfer equation also as in a second case, in an alternate way, where the first term has no meaning or very little importance, the second term has the primary importance. If I want to determine SST, the first term has the primary importance, second term is almost 0. If I want to determine the vertical temperature profile of the atmosphere, the second term becomes the most important. Because that is the contribution of each layer of the atmosphere that is radiating and getting transmitted so that the radiant energy can reach the satellite. Yeah. So next one. Okay, in a very simple way, I will try to explain in a very simple layman terms. Suppose I have, let's take carbon dioxide, which we all know is a very uniformly mixed constituent of the atmosphere, up to 80 kilometers at least. Of course, we are not really concerned about the temperature above 80 kilometers. So it's a uniformly mixed constituent of the atmosphere. It has a typical value of about 410 parts per million. That is the amount of CO2. And we all know this has been growing. The amount of CO2 is increasing over the last 200 years, and that's a cause for concern because it contributes to global warming. So let us take this carbon dioxide. It has a very strong absorption band at 15 micrometer in the infrared portion of the electromagnetic spectrum. So if I have a very strong absorption band at the center of the band, 15 micrometer, essentially what it means, suppose I take a layer of atmosphere very close to the earth. It is radiating in 15 micrometer CO2 absorption band. So the layer immediately above that is going to absorb this, because any good emitter is also a good absorber. So it's going to absorb. So this radiant energy radiated in the lower portion at 15 micrometer will never reach the radiometer in the satellite. Am I making sense? On the other hand, if at the upper regions of the atmosphere, I have atmosphere radiating at 15 micrometer at the strongest absorption band of CO2, there is very little atmosphere above that to absorb that. And hence, there is more likelihood of the contribution of the radiation received at the radiometer in the satellite to come from upper regions of the atmosphere. Instead of 15 micrometer, where I have the strongest band, I look at the wings of the band. Not at 15 micrometer, I look at 15.4 or 14.6 micrometer. Now here, the absorption is not very strong. So then, there's more likelihood of this coming from the mid-troposphere, the middle portion of the atmosphere or the lower portion of the atmosphere. So in essence, this is the essence of the whole temperature sounding or obtaining the temperature profile of the atmosphere. Wherever you have strong absorption, the contribution has to come from essentially upper layers. Wherever you are having absorption on the wings of the strongest absorption band, the contribution can come from the other regions. So this is, in a very simple terms, this is the essence of the inverse sounding of the temperature profile. Next one. So just go back. Yeah. So you can see the x-axis wavelength, and this is the transmittance. So you can see that large transmittance means, what does it mean? Large transmittance means very little absorption, right? So wherever the transmittance is minimum or low, you have very strong absorption. You can see 15 micrometer absorption. Can you see that 15 micrometer? It's written CO2. You have a very strong absorption band at CO2. You also have H2O has a strong absorption band at 6.3 micrometer. That also you can see here. So these are all, this is transmittance, so it can give you a sense of what are the strongest bands, absorption bands corresponding to the various constituents of the atmosphere. Next one. Now this is a hypothetical profile that I have shown on the right-hand side panel. So y-axis is the height in kilometers. So it runs from about 20 kilometers. X-axis is the transmittance. So what you see is from 0 to 5 kilometers, transmittance is 0. From 5 to 10 kilometers, transmittance is increasing linearly. It's a straight line. And then from 10 kilometers till 20 kilometers, transmittance is constant and has a value 1. Now, in deriving this radiative transfer equation that we showed in one of the previous slides, we had implicitly assumed, which is reasonably holds good in the thermal infrared portion, that there is no scattering. We are neglecting scattering and looking only at, so if you remember, reflected or scattered plus absorbed plus transmitted is a total radiation. So now if I neglect or ignore scattering, then whatever is absorbed plus whatever is transmitted must be my total incident radiation. Now, so from 0 to 5 kilometers, transmittance is 0. So A lambda plus tau lambda is equal to 1. So tau lambda is 0. That means A lambda is 1. A lambda is 1 means absorptivity is 100%. That means the atmosphere completely absorbs between 0 to 5 kilometers. Now, if it is completely absorbed, it will radiate, right? But then because its transmittance is 0, whatever it emits cannot be transmitted and did not reach the satellite at all. So, from 0 to 5 kilometers, whatever is radiated will not reach the satellite. If you look at from the height 10 kilometers to 20 kilometers, transmittance is 1. That means the absorptance is 0. Absorptance is 0 means there is no absorption of the atmosphere. If there is no absorption of the atmosphere, there is going to be no emission from the atmosphere. If there is no emission from the atmosphere, there is no possibility of the satellite measuring radiation in that wavelength band. So, we are left only between the atmosphere from 5 km to 10 km. Here the transmittance is varying linearly, increasing with height. So what does it tell us? It tells us that different layers of the atmosphere, different percentage of the initial radiation is transmitted. So that essentially tells us, since the transmittance is neither 0 nor 1, the absorption is neither 1 nor 0. So the absorption is going to have a value which is neither 1 nor 0. So this is the portion from 5 kilometers to 10 kilometers where the atmosphere is absorbing. And the atmosphere is absorbing in this region, height region, it's going to emit in this height region. If it's going to emit in this height region, and then above that you have transmittance is 1, so the emitted energy will be transmitted and this will reach the satellite. So in a very simple example that I have described here, whatever is a radiation received by the radiometer in the satellite should essentially come from the layer which is lying between 5 kilometers and 10 kilometers. This may look very simple, but this is the essence of this temperature sound. Next one. Next slide. Okay, so these are some mathematics I just kept. So this is another form of the radiative transfer equation. Again, the first term is the surface contribution. The second term is the atmospheric contribution. So the delta tau is what's called the weighting function. Next one. Okay, so this is, I'm just finishing. Yeah. So the same example, so the weighting function, you can see it is non-zero between 5 to 10 kilometers. So that means the contribution to the atmosphere is going to be non-zero. Next one. Okay, so this is how the atmospheric profile is obtained. Next one. So now once we have the atmospheric profile, the radiation received in the satellite is because of some of the constituent of the atmosphere radiating. Now we took CO2, we took the strong absorption band of CO2. Now CO2 is uniformly mixed. Because it's uniformly mixed, we know the absorption coefficient and all, so we can determine from the knowledge of the radiant energy, we can find out the temperature of the radiating atmosphere. Now I want to find out what is the moisture profile of the atmosphere. Now the moisture, as you all know, humidity is not uniform in the vertical. You have more humidity at lower levels because the source of humidity is the land, right, or the oceans. So we use the same principle, we determine the temperature profile and then use the same principles of radiative transfer and find out the water vapor or the humidity profile. Yeah, next one. So this is exactly what I was trying to tell you. Can you go back to the previous slide? So you have strong absorption band at 15 micrometer. That is going to tell you, give you the information over B. And the wings, you are going to get the information on A and C. Okay, next one. So this and all I have already touched upon. Next one. Yeah. So difficulties, can you go back 2 slides? So suppose I have, let's say I have 20 bands in the radiometer. One at the center of the strong absorption band and let's say 10 on either sides, 9 on one side. And so I have 20 bands which are measuring radiant energy coming out from the atmosphere at 20 wavelengths. Now if these 20 bands correspond to 20 layers of the atmosphere, there's a one-to-one relationship between them. Absolutely, the inversion problem would be very simple. But as it turns out, each and every contribution of radiant energy received by each band corresponds to a fairly deep layer in the atmosphere. That is what you saw in one of the previous slides. And because of that, this inversion poses serious and very, very complex and computationally very, very difficult situation. Next one. So these are some of the difficulties I've highlighted. Yeah, next one. Okay. See, these are some of those weighting functions associated with the GOES satellite, geostationary satellite. Next one. So this also I've touched upon. Yeah. Yeah, next one. So next one. So all these things I've touched upon. So importance of computers, as I was telling, the first computer was put in place at the Institute of Advanced Studies, Princeton in 1945. That computer name was called ENIAC. The first task given to the computer was to forecast the weather. And the first successful weather forecast happened in the year 1950. Next one. Next one. So importance of computers in weather forecasting, I'll just touch upon 1 or 2 things only. So there's something called data assimilation. Because of want of time, I'm not able to get deeper into it. Essentially, it is like, so the number of numbers which we need to give a global forecast to the initial state of the atmosphere is something like 10 power 7. But the number of observations are 4 orders less, 10 power 3. So how do we resolve? How do we get 10 power 7 observations when we have only 10 power 3? So this data assimilation method provides us a way to do it. This is actually one of the results from information theory. Next one. So if I have a model, an atmospheric model, and if I prescribe the initial state of the atmosphere, in principle I can integrate the model numerically and then find out what is going to be the state of the atmosphere at a later time. This is called the weather forecast. Now, if I were to do it just once, because there are lots of issues with the initial condition, because we don't have adequate number of observations, we also have issues related to the model themselves. So there is some uncertainty, or there's a lack of fidelity of the models when it comes to forecasting. So instead of that, suppose instead of having one initial condition, integrate the model once to get a 24-hour forecast, I get one forecast. Instead of that, if I create 100 different initial conditions, by perturbing the initial conditions and create 100 initial conditions, and I have the computational power, with each one of the 100 initial conditions, I will integrate the atmospheric model, I'll get 100 forecast. So the average of the 100 forecast, it is expected to be closer to the real atmosphere than a forecast coming out from one numerical integration of a single initial condition. So this is called the ensemble forecasting, and it's the computational power that is giving the atmospheric scientists the ability to do ensemble forecasting at an operational level. I think that's about all. Thank you for being so patient. So I guess if there are some questions, and if time doesn't permit it, you can talk to me at a later stage also. It's fine.
Thank you, sir, for your valuable insights. Now, I feel privileged to introduce our second keynote speaker, Dr. Chan Myoki. Professor Chan Myoki is the Deputy Dean of Research at the Faculty of Engineering, Segi University, Malaysia. Her expertise lies in sustainable wastewater treatment, nanomaterials, and the integration of artificial intelligence in environmental engineering. She has led numerous interdisciplinary projects and international collaborations, particularly in nanoparticle-based water purification and predictive modeling using machine learning. Dr. Chan is also the chief editor of the Journal of Engineering and Technological Advances and plays a key role in organizing conferences, workshops, and student mobility programs. Her work bridges academia and industry, advancing innovations in sustainable engineering solutions.
We are honored to welcome Dr. Chan, Deputy Dean of R&D, Segi University, Malaysia. Ma'am, we now invite you to take over the session, preside over it. Thank you.
Hi, good morning to the participant here from India. Just want to check with you. Can you see my slide or can you hear me?
Yes, ma'am. We can see.
See my slide in the full screen, right? Yes. All right. Okay. Just give me a moment. Okay, so again, good morning to the participant from India and a very good afternoon to the participant from Malaysia. So I am Chan Yao Ki, so the Deputy Dean of Research of the Faculty of Engineering in Segi University. So here I would like to thank the colleague at United Institute of Technology for inviting me to this conference, a one-day United International Conference on Technology, Research, Product Development, and Space Science. So today I will share with you my research on AI in wastewater treatment. All right, so before I begin, so just allow me to introduce you our country and my university. So we are from Malaysia, located approximately 4,000 km from India by air and also 6,000 by roads. So I'm not sure how many of you have been here, Malaysia before, but I'm sure that you have heard of our Petronas Twin Towers, which located at the Kuala Lumpur City Centre. And also we are famous with our durians, which is known as the king of fruits. Right, so the video here show you our campus, Segi University. So we provide program range from social sciences, engineering, and to health sciences. So please feel free to pay us a visit if you come to Malaysia. Okay, so now let's focus on our topic today. So, which is AI in wastewater treatment, transforming nano iron copper nanoparticles innovation into smart solutions. Next. All right, so with the growth of populations, expansion of our agricultural activities, industrial developments, and the poor in the enforcement of environmental law, right? So we are facing water scarcity issues and also severe water pollution issues. Okay, so what the engineer have done in the past few years, all right? So what we have done is we adopt these traditional methods, okay, which mainly adopt physical method to remove large suspended solid, such as sands in the sewage to grid retention and filtrations. We also use biological treatments to remove dissolved and suspended biological matter. Okay, so these methods are very matured, easy to operate, and low cost. But there's one problem here is the performance is unstable. So it is unstable is because of the microbe sensitivity to the change of water quality, such as in pH, dissolved oxygens, and also the temperature. So we do have advanced methods such as membrane separation, Fenton reaction, nanotechnology, and adsorptions. So these methods are very efficient in treating sewage or other type of wastewater, but it comes with one cost, which is very, very expensive. All right. So what do we do then? Okay. So here we are synthesizing we are synthesizing iron copper nanoparticle in the immobilized form, right? Okay, so iron copper are the most abundant material on the earth, right? And then the nano size of the material will allow us to treat the pollutant using a small quantity of material. Means that we can treat the water up to the discharge limit by using a small quantity. So by using the small quantity, it will help to reduce the cost. At the same time, we also make it in the form of, we immobilize the nanoparticle. This will easy for us to recovery and reuse the nanoparticle. So again, it will contribute to reducing the treatment costs. And we also take the approach of using adopt machine learning into our research to estimate the water quality. Okay, so here, let me share with you the performance of the immobilized iron copper nanoparticle. So in our research with the local sewage company, we managed to treat the sewage, which is highly polluted in ammonia and also organic matter, by using only 60 grams of immobilized iron copper nanoparticles. And the sewage with flow rate is at 15 milliliter per minute. Okay, by using this operating condition, we managed to meet Malaysia's sewage discharge standards. Okay, then next. Okay, you may have questioned like how stable is this immobilized iron copper nanoparticle? How many times it can be reused, right? So what we have done is we inspect the sample virtually, which you can see from this picture here, right? Then we conduct leaking tests. We also did material hardness test and also the reusability test. So the result shows that the iron copper nanoparticle is stable for a minimum of 25 cycles. So you may ask, why 25, right? So the 25 here is not my lucky number. We conclude that it can be used up to 25 cycles is because we are only managed to conduct 25 cycles of experiments. Okay, but personally and scientifically, I believe it can last for a longer periods. So just to share with you that we did synthesize the nanoparticle like 5 years ago, and now I use the nanoparticle which we synthesized 5 years ago and run the experiment. So the result shows that the nanoparticle still can be used. Okay, so what does this mean? This means that our nanoparticle is very stable and suitable for practical application. Yay! Right. Okay, then next, this is about the AI elements. Okay, so what we have done is we incorporate AI into our sewage treatment. We adopt this RNN, recurrent neural network, okay, to estimate the water quality. I mean, the treated water quality. Okay, we use two different approach. One is we are adding 3 input, which is ammonia, nitrate, and nitrite concentration into the model. And we use the model to predict 3 output, which is also nitrate, nitrite, and ammonia. Then we compare with the 1-to-1 input, which is nitrate to nitrate, ammonia to ammonia, and nitrite to nitrites. All right. So what's the result shows that? So the result shows that the 3-to-3 models, okay, give a better prediction compared to the 1-to-1 model. As you can see from the graph here, the table and the graph here, right? The 3-to-3 model can give us the R-square value up to 0.91, and compared to the 1-to-1 model here, okay, we can get the maximum of 0.83 only. Why is this so? It's because the 3-to-3 model has more input, which make the model more stable, right? So here also shows that we managed to forecast the sewage quality up to 7 hours. Okay, this also means that we can monitor the water quality by using this model, okay, and minimize the use of reagent or sensor, which normally will cost us a lot. Okay, so here comes the conclusion. So by using immobilized iron copper nanoparticle, our team managed to solve the water pollution issue by having this small plant footprint of using these nanoparticles. And by incorporating AI into the wastewater treatment, we managed to reduce the manual sampling, reduce the reliance on expensive sensor, and also reagents. So this eventually will help us to reduce the cost, which also bring this technology one step closer to the practical applications. So here's the paper that I have published in the recent year. So if you are interested, so you can scan the QR code here and read our paper. So here, thank you for your time. Right, so so my research area, as introduced by our chairperson just now, so it's more on nanoparticle wastewater treatment and also machine learning. So if you would like to work together with me for some research project, so please feel free to contact me. Thank you very much.
Thank you, ma'am, for sharing your thoughts with us. Every great event is made possible by the dedicated individuals behind it. To extend our heartfelt appreciation, I invite our principal, Dr. H. Abdul Rauf, sir, to felicitate our distinguished guests.
Good morning to one and all present here. As we say, dreams come true. We dreamed by the month of January, and today, May 28th, it has come true. I'm very happy to stand before you to do a felicitation presentation. Honorable Chief Guest, distinguished scientists, esteemed researchers, industry leaders, delegates, media members, and my dear professors and students. It is both an honor and a privilege to stand before you for this gathering of brilliant minds at the United International Conference on Technologies, Research, Product Development, and Space Science. Today, we come together at the intersection of innovation and discovery, where the boundaries of human knowledge are being pushed further than ever before. Now, we are in the era of AI-driven transformation. We are living in an age where artificial intelligence is no longer just a futuristic concept. It is the driving force behind revolutions across every field, from healthcare to space exploration. AI is accelerating research, optimizing product development, and unlocking possibilities that were once unimaginable. In technology, AI-powered algorithms are reshaping industries with robotics and automation, predictive analytics, and intelligent decision-making. In research, machine learning models are analyzing vast data sets, uncovering patterns, and speeding up breakthroughs in medicine, climate science, and materials engineering. In product development, generative AI is enabling rapid prototyping, reducing costs, and personalizing solutions for global markets. And in space science, AI is guiding autonomous rovers on Mars, processing astronomical data to discover exoplanets, and even assisting in mission planning for interplanetary travel. the motive of the conference, collaboration for a smarter future. This conference is not just about sharing knowledge. It is about collaborating across borders and disciplines to solve humanity's greatest challenge. Whether it is sustainable energy, space colonization, or ethical AI governance, the discussions we have here will shape policies, industries, and scientific endeavors for decades to come. Also, a call to innovate responsibly. As we embrace AI's potential, we must also address its challenges. Data privacy, algorithmic bias, and the ethical implications of autonomous systems. The responsibility lies with all of us, researchers, policymakers, and technologists, to ensure that AI evolves as a force for good, benefiting all of humanity. To conclude my speech, to the organizers, thank you for creating this platform where ideas converge and innovation thrives. To the participants, your expertise and passion are the foundation of progress. Let us use this conference to forge partnerships, inspire breakthroughs, and ignite the next wave of technological and scientific advancements. Together, let's build a future where AI, space exploration, and cutting-edge research lead us toward a smarter, more sustainable, and interplanetary tomorrow. Thank you, and I wish you all an enlightening and productive conference. And a special thanks to Segi University and College, Malaysia, and ISRO Space Tutor Center, UIT, and our college for celebrating and collaborating with us for this one-day international conference. Thank you, one and all the best.
Thank you, sir. Now it's time to honor our delegate. I request our dignitaries to present a memento to Professor A. Chandrasekhar, sir.
To provide an overview of this day proceedings, I now call upon Dr. P. Sindhuja to present the conference schedule.
Hello again. I'm not going to take much of your time, so let me tell you the gist of what is going to happen today. So we have an offline session followed by this. So offline participants, please have your refreshments in the green net and hurry to hall number D102, where you will have your offline session, which will be chaired by our chief guest, Dr. Chandrasekhar. And you have 2 online sessions running in parallel today morning at D108 and D109 respectively. One online session chaired by Dr. Arun Kumar from Sri Ishwar College, and the other online session running in parallel by Dr. Rajalakshmi from NGP College. And in the afternoon, we have 3 online sessions and chaired by Dr. Ashok Gopalakrishnan, Dr. Arun Kumar, and Dr. Rajalakshmi. So this is going to be the gist of it. We have around 80 to 85 papers to be presented in online sessions and in offline also. So all the best, dear participants. Hope you have a wonderful and a productive conference today. Thank you.
As we conclude this segment, let us remember that knowledge shared today will shape tomorrow. Let us engage, explore, and elevate our discussions in the sessions ahead. Wishing everyone a productive and insightful conference. Thank you.